Good morning. Welcome back to today's lecture, and we have been learned many things as we move on into the lectures. So we have discussed the various aspects: operation, transmission types, ray diagram, kinematic diagram, teeth calculation, gear failures, gear material selection, and we have done the model calculation as well. Now we are going to discuss about the shaft design, its overall shaft design aspect, and if time permits, we will discuss about lubrication selection as well. Right, and this is the problem. So if we can do the tick, lot of tick, done the gear type, ray diagram, kinematic diagram, suitable material for main. For gears we have done that, but we have not done for the main and lay shaft aspect. This is yet to be done, carried out. Bearing selection also need to be done, lubrication also need to be done, and heat losses and gearbox casing. So these parts need to be covered in forthcoming lectures. Right. The purpose of the shaft is the shaft transmit rotary motion one end to another. They can transmit rotary motion sideways by arrangement of gears, pulleys, belt, sprocket and chains. Loading can be different. The shaft generally is subjected to combined loading. They can have a torque, bending loads and axial loads also. Okay. So all loads could fluctuate in shaft. So shafts are designed using a concept of fatigue aspect, which is a dynamic failure aspect. We have to do the shaft design. Right. Look at this. This is the typical transmission system. You can see various shafts, right? This is represent what shaft? It's a camshaft. This is your camshaft. You can see the various aspects, and this would be your crankshaft, right? This is for crankshaft. This is, you can see that this is spline shaft for from clutch to gearbox input, right? And you have this another shaft, it is the lay shaft. Right. Finally, you will have a main output shafts. Main output shaft. Look at this, in the transmission itself you are having so many shafts. Of course, the one is missing is a reverse gear shaft, the smaller one, which is not showing in the picture. Okay, even though the diagram shows the uniform diameter, in actual application the diameter will be very different. You can see this is your typical, what is it, crankshaft, right? You can see the crankshaft, and wherever you see the holes, right, you can see this is very shiny, which is for the zonal bearing aspect. So the lubricant will fall through that one and try to minimize the friction wear. That's one thing. This is your camshaft, right? You can see the camshaft. So these are the lobes to operate valves for fuel aspects, inlet valve and outlet valve. In between you may have, these are the called zonal bearing. Okay, zonal bearing. This is the shaft and you have a ring. So that's why this is called zonals. Usually they are the one will subject to very high wear rate, wear and friction. So normally this type of portion where contact happens, right, those will have a higher hardness compared to in between this non-contact area, right, even including the lobe also. So even though you shaft have, wherever you have a zonal bearing aspect, that would be higher hardness, okay, compared to the rest of the parts in the shaft. And this is taken from advanced vehicle technology by Heinz Eisler. You can see this is a 5+1 double stage gearbox. Double stage means input and output will be riveted gate aspect. So, this is your reduction, right? This is your reduction, and this is your shaft coming from your clutch. This is the clutch, and this is your lay shaft. You can see that the lay shaft is clearly given. From there, you will go, it goes to main output shaft. Main output shaft. Okay. So, when you observe this diagram, what do you think of it? Okay. Look at, don't you think your lay shaft is much bulkier? If you look at this, the lay shaft is much bulkier compared to your main output shaft, because that is the one it take the entire power and transmit to the main output shaft. That is one aspect. And also another question, do you see the gear, do you see the shaft diameter is uniform for the lay shaft? You can see that? No, right? It is a variable, right? If you have uniform shaft, what happened? Uniform diameter of the shaft, then the shaft dia is very heavy and mass also is going to be add, which you do not want to, right. So, wherever the load act, that portion alone you can maintain the diameter, the remaining portion you can minimize it. By doing that, you are optimizing the shaft diameter at the load acting positions, such a way that the volume and weight will be reduced. Okay. And actually this is the synchro mesh arrangement. Look at that. So, anything indicate in this symbol which is for the bearing aspect. These are the bearing which are supporting the gear, that arrangement you can see that. And interestingly, if you look at the lay shaft kind of, this is the bearing, you can see that there is a nice taper roller bearing at the end, right. Here also you can see the nice taper rolling bearing is there. So, that means it is like kind of simple supported beam arrangement. Usually the lay shaft is simple supported beam arrangement, whereas if you look at your the main output shaft, it would be like a overhanging. It will be like overhanging. This here is, it is a fixed, somewhere in this position is fixed. As you move on to the from left to right to left, there is no support, right, only the bearings are there, right, there is no support. So, it is kind of overhanging a beam or cantilever, you can say that. So, that is the arrangement you will have. Okay. Let me ask one more question. So, what the loading aspect, do you find any difference between the lay shaft as well as the main output shaft? Is it question is clear? The loading aspect, just think about. As we move on, I will give explanation. Okay. So, you can see this is the shaft configuration, automatic transmission, the input shaft coming from your clutch, then main output shaft, this single arrangement. Okay. And this is the counter shaft, and of course, you could see here this is the input shaft and output shaft, another input shaft, and this is actually your lay shaft. It is all steps. Okay. These are, we will have steps. Then we will move on to the shaft material. Generally, material property must be such that the deflection must be as small as possible. If you have too much deflection, that is not good. So, the misalignment will happen. Okay. So, you have to careful by selecting the material, deflection must be small. So, generally we will use for high Young's modulus material, in particularly steel is a good choice. Normally you can go for ANSI 1020, 1050, called as a low carbon steel. They have high strength and usually high Young's modulus with a small deflection. What do you mean by ANSI? What do you think of it, ANSI? It is a standard, right? What is that? Then we have other material, ANSI 1340 to 50, 314050, so on. 4000 series, you can see the 5000 series and 8000 series, which are alloy steels for higher strength purposes. If you have operating in corrosive environment, then you have to use the stainless steel to minimize the corrosion effect, right? And you have to use a carburized grade. Carburized means you are strengthening the material by inducing carbon content, right? So again, the NSA 1020, 4320, 4820, 8620 will be useful. Okay, if the shaft is to be used as a journal, remember one of the shaft area I have seen, wherever you have polished one with the hole, that is will have a rubbing action against your shaft is there, you have a ring also, inner race. So that will be rotating and make a contact. So obviously wherever you have interaction, it's prone to wear. So that's the reason whenever we have a journal bearing arrangement, we need to give higher hardness. Now you know that portion alone why we are giving a carburized grades, right, for higher hardness purpose. If properties only some of the other materials, usually I will give the table C10, which is taken from the Robert Norton, right. You can see this is taken from the machine design by Robert Norton. You can see all the material combination, ASI or SI, both are same. Depends on the condition, rolled, right, hot rolled or cold rolled or quench and tempered, keep on moves, you can see here. Then element on shafts, okay. So usually you will have bearings, right. The rolling element bearing and journal bearing, steps on the shafts accommodate element such as bearings, sprockets, gears and pulleys. Key snap rings and cross pins to secure elements on the shaft to transmit the torque or prevent things from moving axially. So you have a shaft, remember when you have a constant mesh, usually you need to fix the bearing first, on top of that you will fix the gear, right. So by doing that you have to make sure that the contact between the shaft and bearing is be secured. If it's not secured, they may move axially either left to the right side, that is not good. So okay, so in that, to avoid that, you will have a circlip, usually we say in bearings, keys and snap rings should be provided to prevent any axial movement. So as I said earlier, the diameter may not be uniform, so it will be keep changing. So when you keep changing, it will be step down, right. When you have step down, you will have sharp corners, that is not advisable. The sharp corners will act as a stress riser or stress concentration. So you have to take care of those things while designing the shaft diameter. So grooves of snap rings, holes for keys and cross pins causes stress concentration. So while designing, we must consider this aspect, stress concentration factor. I am sure you would have studied your undergraduate course, KS, KF, KF, right, those factors will come into the picture. Shaft stresses, okay. So you will have a main three important stresses. Normal stresses from bending aspect, then you have shear stresses from bending, then shear stress due to rotation, torsion, and also you will get axial loads due to axial stress due to axial loads. Okay, let me ask a question. If you have spur gear, what type of load the shaft would experience? Sorry? Bending and torsion. Okay. Suppose if I give you instead of spur gear, you are getting helical gear, what do you expect? You will have axial load also, because the helical will have another load component which is axial component that would act on the shaft. So you have to be careful, depends on the what type of gear you are going to use it, then based on the gear get the loads, different loads, talking about the bending and right, the torsion as well as axial loads. Right. Since the shafts have a high length to diameter ratio, the stresses from the bending is negligible. That is what we are going to do that. When compared to shear stress from the torsion, obviously the shear stress will be more crucial than your bending. And the bending loads, you can, this is standard equation, your sigma A equal to Kf MA R and sigma m. I just wanted to inform you what is sigma A and sigma m. This is a mean stress, sigma m is the mean stress and sigma A is the what? Yes, amplitude, right. So, that is the thing. So, this is shaft is subject to fatigue load. So, you always think about with respect to sigma A and sigma m, right. Ma is the alternating moment, mm is the mean moment, r is the distance of the outermost fiber, which you know that, okay. And with the kf and kfm are your stress concentration factors. Please refer for more details Robert Norton machine design book, okay. They have all the information. Similarly, for torsion, the standard equation, right, tau equal to kf into Ta by Rj. Ta is your alternating torque, R is the radius, you know that, radius of shaft, and this is your alternating, right, shear stress, and J is the polar moment of inertia, okay. So, that you should know that. And similarly, for the mean shear stress, you will have a Tm, the same thing, you are only replacing with the corresponding torque and stress concentration based on the alternating as well as the mean aspect. And this is for axial loads, a very simple equation, force by area corresponding your stress concentration factor. These are the equation, and of course, since this is what do you call it, dynamic load, right, dynamic failures, you have to follow the equation. Remember, this is where we are talking about your mean stress and this is alternating stress. And what do you Sy means? Sy means yield strength, right? Sy is the yield strength. Se means endurance strength, okay, and Se is the endurance strength, right. Sometime you may have Sf also. What do you mean by Sf? Fatigue strength, fatigue strength, okay. And question is yield strength only for steels, because your SN curve will have a sharp knee. Remember, this is SN curve, right, this is SN curve, and this is your number of cycles, assuming that this is your stresses. So, anything will have a sharp knee, right, there you talk about your endurance strength aspect, right. So, this is for steels, usually this is applicable only steels. For non-steels, other than steels, okay. So, the curve would be like this, I am sure you would know these things, your stress and your number of cycles. So, there we can't find out exactly where is it. So, in that case you go for a fatigue strength. So, here the fatigue Sf will come into the picture, here Se will come into the picture. This is a major difference between steel and non-steel materials. Okay. Generally, which one use, preferred to use? It is a Goodman equation or modified Goodman equation or Soderberg equation for the shaft design. It depends on the material, right, whether is a, what is the material you will say, right, no, that is a steel is the material I am talking about with respect to ductile material or brittle material, based on that those things again will change. So, this again you need to brush your failure theories, yeah. So, sorry, we are going to have a develop equivalent alternating mean stress, which is sigma m and sigma A, both we need to do. Then using fatigue criteria, either Goodman line or ellipse, depending on the type of the loading and type of material, the shaft diameter will change, okay. And general consideration shaft design, you can see that always the shaft should be as short as possible, that is one thing you need to do that. Shaft arrangement should be simply supported beam rather than the cantilever beam, then the stability will be much better, stability would be much better. Allow shaft have a better stiffness by mass ratio and a higher natural frequency than the solid one, okay. Hollow shaft is always better, because you are reducing the mass. By reducing the mass, what happens? Your natural frequency, you can increase it. So, have you heard about natural frequency? When you operate shaft matching with the natural frequency, what do you expect? Resonance. So, you do not want to operate your shaft dia closer to the resonance. So, better to have hollow shaft would be preferable. Keep stress riser, I am talking about stress concentration, away from the larger bending moment regions to minimize their effect with the providing generous radii and reliefs. Generous radii mean instead of having a step like this, we will have sharp corner. Better to remove gradually like this. By doing that, you avoid stress concentration. Okay. Lower carbon steel may be preferred metal since it is the highest stiffness, which already I have mentioned that. General consideration of again continue. Deflection gears should not exceeding point. It's a general thumb rule 0.127 millimeter and relative show between the gear axis should less than 0.03 degree. If you have a bearings, when you say sleeve, it is indicate about the journal bearings. The shaft deflection across the bearing length should be less than the oil film thickness. Okay. What do you mean by oil film thickness? Do you know how does the journal bearing operates? How does the journal bearing operates? Any idea? So, you have a shaft, right? Assuming this is the shaft, right? Okay. Then there is a ring also will come into the picture. This is the thing. By rotation, right, due to squeezing action, the film will develop the pressure and lift the entire rod. That is called nothing but hydrodynamic effect, right. So, the oil film should, you will have oil film. That oil film, what I am saying, the shaft deflection across the bearing should be lesser than the oil film. If the deflection more than the oil film, what happened? You would not have a hydrodynamic effect. So, that is the information, you have to pay attention when the part of the shaft used as a journal bearing. If non-self aligning rolling element bearings are used, then the shaft should be, you can have little more allowance 0.04 degree. Non-alignment means non-aligning. So, bearings, there are so many bearings are there. Self-aligning bearings, deep groove ball bearing depends on the generally bearings for axial load, but you may have make a pardon, generally bearings for radial loads application aspect. If you have axial load, then you have to take care of that. So, whenever you have axial load, then the alignment will change. To take care of that, you can have a self-aligning ball bearing, magnetic bearings and the deep groove ball bearing, those things can be used such a way that it will give a little more fluctuation to have a higher slope 0.04 degree. The first natural frequency, the shaft should be at least 3 times higher than highest forcing frequency expected in service. Obviously, this is to avoid any resonance, right. Now, you know that why we wanted to forcing to better to choose the hollow shaft than the solid shaft. Okay. So, this is the standard equation, you can see that this is for the steel, okay, this is for the steel and this is for non-steel. I am sure you know MA means moment, alternating moment, the corresponding torque, and this is again similarly for, you can see this is MA for alternating and the corresponding mean thing you can see here. NF is nothing but your factor of safety. NF is the for the shaft aspect, factor of safety. And interestingly, look at SE is given, endurance limit strength is given for the steels, whereas SF is given for the non-steels. These are the two equations. Okay, it is given a torque constant and the bending is fully reversed. So, where do you expect torque constant and bending is fully reversed? Where do you expect? Right. My question is, where do you expect? Assuming that this is coming from the my input shaft, this I am talking about right. From there, I will take the lay shaft. this is my lathe shaft, it moves on. Okay. So the reduction will happen here, the reduction is happen here. Remember, I am talking about the lathe shaft. So what happened to the torque in lathe shaft? Torque is constant, right? Torque is constant. Torque is constant. How about your bending? How about bending? Is it fully reversed or not? It is fully reversed, right? You are making the contact, right? After that you are leaving. So that means it's a maximum and 0. So right, again going back, it's a fully reversed. Fully reversed. It's a fully reversed. So this is for one minute. Fully reversed. Remember, I think you should know this. Have you heard about these things? What is this arrangement? What do you call this arrangement? And this is 0. So what is this arrangement? There is one more arrangement will come. There are 3 things: fatigue load aspect, right? So this is, which is the fully reversed here? Second one, right? So what about fluctuation? Where is the fluctuation? Somewhere else will go like this, right? So these are 3 arrangement. These are 3 arrangement. So gear, do you expect gear is a fluctuated load? No, it won't be fluctuated, right? So it should be maximum to, right? So check all those things aspect. Okay, this is your you would have studied decimal measurements. Let me ask one more question. Now we know torque is constant and bending is changing. The another question what I want to know, this is your first gear, assuming that the smallest pulley, this is the biggest one, okay, the largest one. I am taking 2 example from the lathe shaft aspect, from the lathe shaft aspect. So torque is constant. What happened to the stresses here? What happens stresses? Right. Which way the load will act? That's another question. Assuming this is my gear profile, right? This is my gear profile. So if you do that, normally you will have in this way, right? This is your resultant Fn, right? This is your pressure angle. If you divide, you will have 2 components. One is tangential Ft will come into the picture. Another one will come into Fr will come into the picture. Fr, your tangential load is there and radial load also there. Both together will have resultant load. So when you do the shaft calculation, you have to split diameter into 2 components. One is vertical component and horizontal component. Right. I think this is the way you should have do the diameter calculation. So what you have to do? You take the Ft alone. Ft will be horizontal, right? Ft will be horizontal. So that's one thing will be there. I am just for indicating alone. Then this one will be radial, right? Similar way you will have one Ft and one radial. So what we have to do? So whenever you do the calculation, you take the particular gear, right? You take the particular gear and apply the load and try to find out what is the diameter and move on to the next. Because torque is constant, but Ft will change, right? The Ft keep changing, Ft and Fr changing. Again that position for that particular gear, you have to find out what will be the moment, right? Then moment try to find the diameter. So this is the way you have approach. You have to approach first to do the split the shaft into vertical and horizontal, and each gear, right, do the calculation and try to find out the moment. Then you do the square root of, I am sure that you know that. Then find out the corresponding diameter based on the constant torque and fully reverse bending thing. Okay, I am just giving you a concept because it will take lot of time to do the solve the problem. Now I am giving another information. fluctuating bending and fluctuating torque. Okay, it's a mean bending, mean torque. Usually we use von Mises to find combined equal alternating mean stresses and use the modified Goodman line equation. My question is, what type of loads would the main output shaft experience? Is torque is constant or variable? Torque is variable. So variable means fluctuating, right? It is fluctuating. Okay, that's one thing we got. Already from lace shaft we know what is happening to the bending also, right? The same thing would reflect to the corresponding the contact reaction forces. So obviously the main output shaft is subjected to fluctuating torque and fluctuating bending, right. So again you have to calculate for the main output shaft individual diameter using this equation. This is equation valid, this is ASME equation, right, is valid only for the fluctuating torque and fluctuating bending. The previous equation is valid for a constant torque and fully reversed earthing, right. So again you could see here MA you have to find out from your beam shear diagram and bending moment diagram. Similarly the other information, and these KF, KFSM all are related to your stress constant factor. Please refer machine design book by Robert Norton is given the complete information. Okay. Now the standard size for the solid shaft. Now you got the shaft diameter based on the calculation, and if you get up to 25 millimeter, okay, even if you get a fraction, you can have increment of 0.5. If the diameter falls between 25 to 50, you can choose 1 mm increment, and so on for 100 to 200 or 5 mm you can do that. Okay. Let me ask one more question. We have done the model calculation, we have done the standard diameter for the shaft. So where is the check to whether our procedure is correct or not? How will you check? Whatever we done the so far calculation, how will we check? Is there any method to check whether whatever we done so far is correct or not? There should be a way, right? Yes, Arshia. Factor of that we are giving factor of safety, right? In the all calculation we have chosen the, remember pitting stress for model calculation we are given the S square H 1.5, 2, 2.5, 3, we have done that. Similarly, we have taken the frame factor psi, right, as structural support psi, different values, and we got the relationship also, that is finding the values. The question is whatever we got the values or whatever we got answer are correct or not, how would we check? What is the way to check? Okay, or how they are related within the design constraint, within the design limit. Okay, so another way is deflection. What we do is check with the deflection. One is shaft deflection. If they meet, they are correct. If not, you have to vary. So this is a given diametral pitch. Diametral pitch nothing but your reciprocal of module. Diametral pitch is usually used in US system, whereas in rest of the countries other than the US will use the model calculation. Okay, it simply says a number of teeth per inch, that is called diametral pitch. Yeah. So if you look at this, the spur gear, when diameter is less than 4, the deflection can have a higher. Then as you move on to the more teeth, then the deflection reduced to 0.125, 0.05. Okay. So these are the one aspect, deflection aspect from the shaft deflections, and another one is rigidity aspect also. You are going to select the bearing and going to fix it, right. From there, what is the slope, right. So, depends on the bearing you select, the slope should be within this limit. If not, again you have to redesign your entire gearbox. You have to redesign interval. Okay. So, there are tapered roller bearing, cylindrical roller bearing, deep groove, spherical, self-aligning and uncrowned spur gears. So, within that this is the self-aligning and spherical will take a more slope which can be adjustable, that is the most preferred. So, normally whenever you have helical, single helical or herringbone, this type of bearings are much useful. Right. Yeah, very importantly, length of the shaft calculation is just for guidelines. The distance between the gear and gear wall you should give a 10 mm. The distance between the two adjacent gear you can give the 5 mm. Remember, I have shown the gearbox, right? Very close the gearbox from the taken from machine design section. You have seen it, right? So, there are the very close you have to maintain it so that the length can be reduced. And of course, for bearing support usually we will take 30 mm. The bearing support means we talk about end of the shafts where you have to give the bearings, right? That will have a 30 mm. And normally for dog clutch and synchro mesh arrangement, right, we will give a 50 mm. Okay. So, that is of course, this this is enough. I am just one point I am missing, your face width. That is also will add up into your shaft calculation. So, if you have first gear, the face width will be higher, second gear will be reduced, and again when you go for a higher fifth and sixth, right, they will slightly increase. Those things need to calculate. That also will come into the picture, right. Altogether, they will give you a length of the shaft, right. Now, we will move on to the lubrication. Okay. Why would we need a lubrication? First question that is come into the picture, right? Yeah. Yes, wear and tear. Okay. See, this is standard equation, right? This is your mu equal to F by W. F by W is given. Okay. I will give a simple example. I have a box, okay, which has the load W, right, resting on one surface, right, resting on a surface, and I try to move in this direction. Okay, when I try to move in the direction, so the resistance will offer to me prevent these things. So, this is F tangential thing, and this is the one which is, this is the normal load W, this is a reaction load, okay, R, which is also W, right. Mu equal to F by W is given, okay, that is the one thing is there. So, another scenario, what I am going to do, that same weight, I am giving same weight, instead I am having a small lubricant, right. So, the same block is there. Let me ask, in this condition, what about my tangential force to move the block will be higher than the dry condition or lesser? Lesser, okay, that is correct. So, I am giving just, this is just maybe take it as a oil, maybe coconut oil, fine. So, this is a F, right, and again you should know that my W's remain constant. According to the definition, a coefficient of friction equal to mu equal to F by W. W remain constant, okay, but just now we know that this mu oil, right, is lesser than the mu dry, D we can say that, okay. So, that can be possible if your tangential force reduced, because the W remain constant, isn't it? So, why the tangential force is reduced? That is the question. I know simply by putting the lubricant, it will improve the object to move easily, right, that is there, but question is how the lubricant influencing frictional force, that is the question, right. So just think about it. We know this is the standard equation, right? This is the standard equation. So what happened your frictional force? Have you heard about shear stress? When the fluid shearing between the as a layer, you will have shear force. The shear force directly proportional to the velocity gradient, dou u by dou y. Remember this one? Then tau equal to eta dou u by dou y. Right? Remember, very fascinating. Your mu is called coefficient of friction. That is resistance offered by the body, right. This eta is nothing but coefficient of viscosity, that resistance offered by the fluid. Can you see the relationship now, right? The same, but the phases are different, right. One we called as a coefficient of friction, the other one is called as a coefficient of viscosity. Okay. Then you may ask question, then what is the relationship? Can I write shear force equal to my tangential force by area? You can do that, right? That is what happening. So the tau you can replace by F by area. Area anyway constant, right? Assuming that. So if replace it, you will get everything with the based on the shear strength. This is what happening. In fact, interestingly, this is the equation. You can see that this is the coefficient of friction, and this is the shear strength of the bulk material, and I indicate about the lubricant film interfacial length. Okay, so that's a ratio. That's a ratio. So higher the you can see that higher the shear strength of the lubricant, what happened to your coefficient of friction? What happened? Can you see the relationship now, right? My question is, if shear strength of the film and shear strength of the base material equal, what happened to your coefficient of friction? Coefficient of friction will be very high. As you keep on reducing, okay, when you are reducing, what happened, right? When you reduce this value, right, the shear strength, the lower the shear strength of the lubricant, your coefficient of friction will be the lower. This is the concept. The viscosity, how the viscosity and the lower ways shear strength are related. Based on that, your coefficient of friction also will be reduced. This is the important thing, please understand that. And right, so then the lubricants, you can have a different lubricants application based on engine oil, gear oils, turbine oils, hydraulic oils, metal working oils. In that again cutting oils, forming oil, then rust preventive, that is also there. Then usually the base the lubricant will consist of base oil, which is mineral byproducts. Then base oil polymerize, usually will have a polymerase or synthesis if it is a synthetic oil. Additives, that is the one will enhance the performance. Okay. So we will have a natural additives, you can have synthetic additives. And more importantly, gear lubrication I wanted to talk about. The purpose of gear lubricant is you need to understand about what is the function is going to be provide. Then properties of lubricant you need to understand. You need to understand what lubrication regime is going to be operate, and selection of lubrication, that is also important. And what is the way you have to apply the lubricant. When you say apply the lubricant, whether you want to use a splash method or bath method or using nozzle and spray the lubricant. So that is also very important thing. And how much volume of lubricant also required for the gearbox, right. So the function of the lubricant is first reduce the friction, it should remove the heat in the contact, and it should able to clean the lubricant detergent, which is additive aspect. And also it reduce the noise by giving the dampening effect. It should provide leakage, prevent the leakage aspect. More importantly, it should prevent wear aspect, right. So these are the main function of a lubricant. and of course this is the kinematic viscosity. Yes, so the viscosity is the important property for the lubricant. Okay, so I think remember I said earlier also, depends on the speed, depends on the speed. If you have a higher speed gearbox, you should go for the low viscous. Okay, and if you have low speed, then you can go for higher viscous. Higher the viscous, the cost of the lubricant expensive. Okay, the reason is, if you choose the higher viscous lubricant for higher speed application, when you speed means, so assuming gear is there, you have taken the very thick coil. If gear is rotating the thick coil for a few minutes, what happened? The sharing between the lubricant will give a internal heating, right? Internal heating will in turn increase the heat. The moment heat is increases, what happened to your viscosity? Reduces. When the viscosity reduces, it's go back to lower level, right? So why do you want to? Anyway, by if you operate your gear higher speed, automatically due to the internal friction, it will reduce the viscosity. So rather spending or using high viscous lubricant, better to use the low viscous lubricant. So that's the reason. So low viscous oil used for high speeds, high pressure, low temperature, whereas high viscous oil used for low speed, higher pressure, higher temperature. So this is what is the standard equation you should use to find out what is the required lubricant. Okay. So this eta 40 is a kinematic viscosity of oil centistroke at 40 degrees Celsius, 7000 by square root of V. V is the mean pitch and velocity. Okay. Remember, you have so many gears. How will you find out? You can take the average pitch and velocity of the shaft and try to find out, and substitute, you will get the V, right. In fact, so again, as a velocity increases, look at this, as pitch and velocity increases, your viscosity also decreases. Remember, okay, that's a thumb rule, basic thumb rule. So higher the velocity, lower viscosity lubricants are preferred, and these are the thing. So once you find out the viscosity and operating temperature, excuse me, once you find viscosity, right, and you know what is the operating temperature, based on that you can select the lubricant what is needed. So normally we use for ISO VG grade. VG ISO is an internal standard organization. VG means viscosity gradient. So we start from 46, 68, 100, 150, 200, so on. Depends on the operating temperature, bulk temperature, you have to select the lubricant. Okay. I think I will stop now. So we will continue next class. Thank you.